Okay, we'll just get going. We have 20 questions to get through, so let's get on the ball. So the exam, if you're wondering, the distribution of questions that I have on this review, and which we also would find on the Blackboard practice exam, is pretty much identical to what you'll see on the real exam. Not saying the questions themselves are identical, but just the topics. So there's 3 chapters, 4, 5, and 6. They are distributed roughly equally, the questions are, but it's probably going to be a little bit more heavily weighted towards 5 and 6 than chapter 4. So I think that's reflected in this review. There's roughly 5 or 6 questions under dealing with chapter 4 material, and then a little bit more of, about 2/3 of the test will then be, a little bit more than 2/3 will be chapters 5 and 6. So it's not perfectly equal, but pretty much all those chapters will be covered pretty evenly. And then, as I said last time we did this review, as I'm doing this, whenever you have questions or want further clarification, either directly about what I'm talking about or just anything that's related to that, please don't hesitate to interrupt me, and I don't mind going off on tangents and things like that. Okay, so let's just go ahead and get started then. The first one is about electron group arrangement and molecular geometry. So we're trying to find that for this anion trifluoroselenide, SEF3-. So this is the first topic we covered in chapter 4, VSEPR, using the Lewis structure to then predict the shape of the molecule. So it's taking it a step further than just doing the Lewis structure itself. So this does require us, as many of the topics do in chapter 4, that we have a good Lewis structure. So when we talk about the molecular shape, when we talk about hybridization, which is another big topic, we have to have the Lewis structure correct first. So remember how we do that is we have to first count electrons. Since we haven't done this in a while, let's pull up the periodic table and see how we count electrons. So we have a selenium and 3 fluorines. So we get the number of valence electrons from the group number. So Se is the number 34, selenium, and that's going to be 6 valence electrons because it's in group 6A. It has an S2P4 valence configuration. And then fluorine is over here, one group over, group 7. So that's going to be 7 valence electrons, so it's going to be 6 for selenium, 7 for fluorine, S2P5 configuration for fluorine. All right, so those are the valence electrons for each of those atoms. We have to add them up then and account for the negative charge. So our selenium, we have one of those, and it has 6 valence electrons. We have 3 fluorines with 7 each. And then remember, whenever we have a net charge, negative, we have to add more electrons. Positive, we have to take electrons away, so that gives us another one. And so we have a total of 28. 28 valence electrons that we then have to arrange in the correct fashion. So we start with our central atom, which is selenium. We add single bonds to each fluorine. We complete the octets of the fluorines first by adding 6 non-bonding electrons, or 3 pairs. So once we've done this, that's 3 octets, so that's a total of 24 of our electrons. We have 28 to use up, so the last 4 then will go on the central atom. So we always add to the central atom last, and that's what we end up with. 2 lone pairs on the central atom to finish up our total of 28 with a negative charge. It's supposed to be a bracket, but that always confuses people, so let's just do it this way. All right, there's a negative charge there too. All right, so then we have to translate this to an electron group arrangement in a molecular geometry. So the electron group arrangement is the arrangement of all of the valence electrons on the central atoms. That's going to include the bonding pairs and the non-bonding pairs. And the electron group arrangement just comes from the total number of electron groups. So we can put this into that AXE notation, central atom, and then the central atom has 3 atoms, 3 fluorines bonded to it, so it's going to be X3. And then it has 2 pairs of non-bonding electrons, so that's going to make it E2. So it's an AX3, E2. And then remember that the electron group arrangement comes from the total number of electron groups, X's and E's. So we call that the steric number. That's one way to describe it. And that's going to be the sum of those 2, which is 5. So there are 5 total electron groups on the central atom. And so anytime there are 5 electron groups, any combination of bonded atoms and lone pairs, that's going to give us the same electron group arrangement when there's 5 of them, and that's going to be the trigonal bipyramidal. So there are several different AXE notations that will have the same electron group arrangement, trigonal bipyramidal, as long as the total number of electron groups is 5. So whether it's AX5, AX4E, AX3E2 is what we have here, AX2E3. Any combination of 5 will give us a trigonal bipyramidal arrangement. And then we have to figure out what the molecular geometry is. So it's trigonal bipyramidal, so that eliminates a few of our answer choices, but we still have 2 choices to consider, and we have to figure out which one of these is the correct geometry. So when we have AX3E2, we're putting all the electron groups in a trigonal bipyramid. So remember that shape is basically a triangle, and then one above and one below the triangle. So there's 5 total electron groups at each of these positions here. And then the first thing we want to put in are the lone pairs, because the lone pairs are the ones that repel most strongly. So whenever we have the trigonal bipyramidal arrangement, all of the lone pairs go on the triangle. So there's 2 of them, they both go on the triangular part. We put the atoms, the fluorines, and the rest of them. And so this one is pretty clearly what we call the T-shaped geometry. Okay, so that's going to be then choice C, which has the correct electron group arrangement, which is trigonal bipyramidal, and the correct molecular geometry, which is T-shaped, where for the molecular geometry we only care about the arrangement of the atoms themselves, and we ignore the lone pairs when defining those shapes. Okay, questions on VSEPR? That's I think the only one we have on this, so if there's anything else you want me to clarify, please speak up. Alright, if not, we can move on then to number 2, which is still related to VSEPR, but it's a little bit different of a question. And here we're giving you a series of fluoride molecules, nitrogen, boron, xenon, difluoride, xenon, tetrafluoride, sulfur tetrafluoride, all these different fluorides, and asking you which ones have a non-zero dipole moment. The first thing we should be aware of is that there's different ways to ask the same thing. So when we say non-zero dipole moment, that's the same way as asking which one is polar. Right? A non-polar molecule has no dipole moment. A polar molecule has some non-zero dipole moment. And we're not asking you to rank those, we're just trying to figure out which ones are polar, which ones, of these choices are going to have some polarity at all. So to do this, we have to consider the molecular shape to be able to do this. We have to look at the 3-dimensional structure and then decide whether there's a net dipole or not. And so for all of these, we do need to consider what the VSEPR shape is. So I'm going to kind of blow through this and not go through all the details, but for every one of these, we need to define the molecular geometry. So NF3 is going to be AX3, so it's going to have a pyramidal shape with one lone pair in the central atom. I'll leave the lone pairs off of fluorine, but they're all there as well. So this is AX3E. And then we have to decide whether this is polar or not. And remember, the idea of whether it's polar is determined by whether the individual bond dipoles cancel out or do not cancel out. So fluorine is more electronegative than all the central atoms that we have here. So there's always going to be a polarity for each individual bond. And when you have a trigonal pyramidal case, the polarities don't cancel out because there's a net dipole pointing down towards the bottom because it's not a planar molecule. So anytime you have one lone pair, if you want to remember it this way, if there's one single lone pair in the central atom, it has to be polar. Because typically what we're going to ask you to do is, like we're doing here, just tell us if it's polar or nonpolar. Nothing more details than that. So if there's a single lone pair in the central atom, it's going to be polar. You don't have to really think about it any more than that. If we look at BF3, which is the next one in our list, BF3 gives us a trigonal planar shape because there are no lone pairs on the central atom. So again, there's lone pairs on fluorine that I'm leaving off, but what we really care about is the geometry, which is determined by the central atom. Here, this is going to be trigonal planar. It has an AX3 electron group arrangement. And so anytime you have 0 lone pairs on the central atom, that's going to be nonpolar, because in all of those basic electron group arrangements, linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, all of those arrangements, if you have dipoles pointing in each of those directions, are going to perfectly cancel out. So in this case, we'll have a dipole pointing towards each fluorine, but they totally cancel each other out. And so whenever you have no lone pairs, this gives you a nonpolar molecule. So BF3 is nonpolar, so it's not going to have a non-zero dipole moment. We have to do the 2 xenon ones now. So XEF2 is going to be AX3E2, so that gives us sort of this shape here. We have a xenon, and then we have 3 lone pairs in this case that all go on the triangle. Our fluorines are above and below. So this is a linear molecule. All linear molecules are also nonpolar, provided that the 2 atoms that are bonded to are the same. So they're both fluorines, so the 2 dipoles cancel each other out. This is AX3E2. sorry, AX2E3. Which is linear, and anytime it's linear, it's going to be nonpolar. All right, so that one's nonpolar, so we cross that out. XEF4 gives us an AX4E2. So we put the lone pairs opposite each other, and that gives us a square planar arrangement of the fluorines. So it's a square arrangement. And this is also nonpolar because the individual bond dipoles cancel each other out. There's one pointing towards each fluorine, but there's also one pointing in the exact opposite direction, so they all cancel. So square planar is another one of our nonpolar geometries. And then the last one here is SF4. And SF4 is also a 5-electron group, but it only has one lone pair. It's AX4E. So the lone pair goes there. Fluorines go there. We have a net dipole pointing towards right to left as I've drawn it. And as I said, whenever there's one lone pair in the central atom, regardless of what the other, the total number of electron groups is, one lone pair on the central atom always results in a polar molecule. So AX2E, AX3E, AX4E, AX5E, those are all the possibilities that have one lone pair. Those will all be polar no matter what the X's are, no matter what the other possibilities are. So then this one's also polar. So these two, NF3 and SF4, are polar, and that corresponds then to answer choice C again. Okay, questions on molecular polarity? Yes? Yeah. Well, so when it's this is an octahedral electron group arrangement. There's 6 in total. So whenever you have lone pairs, the goal is to put them as far away from each other as possible because they have stronger repulsion than the bonding pairs. So if you have 2 lone pairs on an octahedron, you want to put them 180 degrees apart. Now, all of these positions are equivalent, so you could put the lone pairs here and here on the square. It's just rotated, so it's the same thing. It's just this is the easiest orientation to see that it's a square-shaped molecule. So whenever it's 6 electron groups and you have 2 lone pairs, they have to be opposite each other. For 5 electron groups, it's not as obvious why this is the case, but having the 3 lone pairs on the triangle is slightly better than having one of them or 2 of them on the apical positions as well. So it's not as straightforward to see why that is in this case. But for the trigonal bipyramidal system, you always want to put the lone pairs on the equatorial plane 120 degrees apart from each other. It's a little bit better than having them up here where they're going to be 90 degrees apart from something. Yeah. Yeah, so if we said which one of these has no dipole moment or a 0 dipole moment or is nonpolar, those are all the ways to ask about nonpolar molecules. Yep. Mm-hmm. So I skipped a lot of steps here, but then, so this goes back to what I talked about on the first question, where you have to first draw the Lewis structure. And then remember that when we draw the Lewis structure, I'm leaving off all the lone pairs on the fluorines, but those are going to all have 3 lone pairs on them with complete octets, and then whatever electrons are left over go on the central atom as lone pairs. So you have to start with the Lewis structure. There's not really a shortcut to get to these. I just didn't want to spend all the time drawing 5 more Lewis structures and doing VSCPR for all of them. If you want me to go into any of them in more detail, I'm happy to, but it's really the same process that I used on the first problem, where you have to count electrons, draw the Lewis structure, figure out then how many lone pairs are in the central atom and all that stuff. Okay? Yep, in the back.
Is there a number of lone pairs more than one that would be polar?
So the question is there a number of lone pairs more than one that would be polar? And yes, so the answer to that is yes. So there's a table in the notes when I talked about polarity at the very end that lists all of the AXE notations as a function of whether they're polar or nonpolar. That's only true rigorously when all of the X's are the same. But if in terms of the ones that have more than one lone pair, the possibilities for that are, AX2E2 is a common one, and that's going to be polar because it's bent-shaped. And then you have AX3E2 is T-shaped. That's like the one we did up here. That's also going to be polar. But then the only one that's not polar with two lone pairs is the AX4E2. So with one lone pair, they're all polar. With two lone pairs, there's some of each. With three lone pairs, the only one that's really important is that we're going to see in real molecules is AX2E3, and that's nonpolar. So you have to. It helps to know what the geometry looks like and understand it. But there is a table in the notes from that lecture, which would have been somewhere around February 16th, I think, and that's going to have all that information summarized for you. But it's helpful to try to picture it yourself too and understand how these translate from the geometry into the polarity. All right, anything else on that topic? All right, moving along then. Now we're talking about hybridization, and this is on purpose, so I could save ourselves a little bit of time. This is the same structure that we talked about on the first question, SCF3-, and we want to know what's the hybridization of the central atom. So a lot of this falls from what we've already determined for this molecule, which is the electron group arrangement and all that stuff. So as we saw in the first question, which I won't repeat all the details, this is an AX3E2 molecule, and the steric number, or the total number of electron groups, is 5. And whenever you're determining hybridization, it also is determined by the total number of electron groups, with no consideration for whether those are X's or E's or any combination of those. So anytime we have 5 electron groups, we're going to have the same hybridization. And how do we figure out what that is? So remember that there are 6 orbitals that we can hybridize. So the central atom has 1 s orbital in its valence shell. It has 3 p orbitals available for hybridization. And it has up to 5 d orbitals, but in reality we only ever use 2 of those. So we have some d orbitals as well that we can hybridize. And then if we have 5 electron groups, we need to hybridize the first 5 of these orbitals. And so that's going to be, we just pick the first 5, an s, 3 p's, and a d, which gives us sp3d. Okay? So all of the hybridizations that are possible are going to be determined by the number of electron groups. So to summarize that really quickly, the only possibilities are 2 through 6 that really matter for hybridization. So if you have 2 electron groups, you just hybridize 2 orbitals, which is sp. 3 electron groups, you hybridize 3 orbitals, which is sp2. 4 gives us sp3. 5 we just saw is sp3d. And then the highest order hybridization you can have would be sp3d2. Sometimes this is written as dsp3 or d2sp3, but they're the same thing. There's no difference there. Okay, so the idea here is that the number of electron groups is going to determine the hybridization. And again, for hybridization, when I introduced it in class, I tried to give you a lot of the theoretical background about what hybridization is and what exactly does it mean to hybridize orbitals. It's certainly helpful to understand that, but the vast majority of the questions we'll ask you are going to be exactly like this. Just determine the hybridization, and if you can count the number of electron groups, then getting the hybridization from there is really no big deal. Okay, questions on hybridization? Yep.
Where do you get 3 P's?
So remember that when we have atomic orbitals, these are all the atomic orbitals that are on the central atom. And the different orbitals are defined by the value of L. So S is an L equals 0, which means it only has one m sub L value, so there's only going to be one s orbital in a given energy level. But then for the p orbitals, L equals 1, so we can have m sub L is -1, 0, and +1, which is a total of 3 p orbitals at any energy level. And then the d orbitals, there's a total of 5, but like I said, we only use 2 of those for hybridization ever. That can also be determined from the periodic table. So remember that this is the s block. It has 2 elements. It's the 2 columns in the s block, which means corresponds to a total of 2 electrons that can go into s orbitals, meaning there's only one s orbital. The p block has 6 total elements, and that means there's a total of 6 electrons you can put into p orbitals, which corresponds to then having 3 p orbitals available whenever you're forming bonds or doing hybridization. Okay? So that just comes from the definition of the atomic orbitals that we have available on the central atom.
So as long as we can get to the AXE notation, we can just follow that?
Yep, if you can get to the AXE notation, you can follow that. There are some possibly more detailed questions we could ask you, such as things about, sigma and pi bonds, but if you're just trying to find the hybridization, which is most of what we'll ask you to do, just get to the AXE notation and you're all set. Right. All right, number 4 is the last major topic in chapter 4, which is molecular orbital theory. So the first question I have here is just sort of a general knowledge or conceptual question about molecular orbital theory. So according to molecular orbital theory, which of the following will increase the bond order in a diatomic molecule? So remember that one of the key things we can determine from molecular orbital theory is what we call the bond order, which tells us whether it's a single bond, a double bond, a triple bond, or sometimes it can be we had half bond orders as well from molecular orbital theory. And there's a simple equation that tells us that the bond order is just 1/2 times the number of bonding electrons. So when we have molecular orbitals formed from atomic orbitals, we're always going to mix 2 orbitals together and get a bonding orbital and an anti-bonding orbital. And so some of the electrons are going to go into the lower energy bonding orbitals, but then sometimes we also have electrons in anti-bonding orbitals. So if that's the case, the bond order is given by the difference between the two multiplied by 1/2. All right, so that's the equation for bond order. So if we want to think about what happens when we add electrons to either a bonding or an anti-bonding orbital, if we add electrons to the bonding orbitals, we're increasing this part here. So every time we add electrons to the bonding orbitals, every time we add 1 electron, we're increasing the bond order by 1/2. So the more electrons we have in bonding orbitals, the higher the bond order. So adding electrons to the bonding orbitals will increase the bond order. If we add electrons to anti-bonding orbitals, which is the other type of orbital that we can have, in that case we would increase this term in the equation. And so anytime we add electrons to anti-bonding orbitals, we're weakening the bond, making the bond order smaller. Okay? Alright, so the bond order goes up if we add electrons to bonding orbitals. Bond order goes down if we add them to anti-bonding orbitals, so then the inverse is also true. If we take electrons out of bonding orbitals, the bond order will go down. If we take electrons out of anti-bonding orbitals, the bond order will go up. So the opposites of both of these statements are also true. So if we want to look for the ones that will increase the bond order, we know that adding electrons to a bonding orbital will increase the bond order. We know that removing electrons from an anti-bonding will increase the bond order. So 2 of those statements will result in an increase in the bond order. These 2 here, if we add electrons to an anti-bonding orbital, that decreases the bond order. And if we remove electrons from a bonding orbital, which is choice C, that will also decrease the bond order. Okay, so the bond order is determined by the relative number of electrons that are in the lower energy bonding orbitals versus the number of electrons that are in the higher energy anti-bonding orbitals. And then by considering the difference between the 2, we can figure out what the bond order is. Okay, any questions on the sort of the basics of molecular orbital theory? The next question also deals with it, but anything about just the concepts before I move on to that? All right, so another thing we'll have to do with molecular orbital theory is answer questions like number 5, where we're going to give you some diatomic molecule. Now remember that molecular orbital theory is, significantly more complicated than simpler bonding theory. So we're not really going to deal with anything besides diatomic molecules, O2, N2, something, we could add some positive and negative charges in there, but it's always going to be just 2 of the same atom bonding to each other and no more than 2. And so that's going to be the type of molecules that we deal with, and then we're going to ask you things about, bond order, number of unpaired electrons, things of that sort. So here I'm asking you both of them just so we can see how that works. So when we, in this case we have dioxygenyl, that should be cation, not action. There's a typo. It's the cation, O2+. Maybe that was autocorrector. Maybe I just can't type, whatever the case is. We have O2+, and we want to know what's the bond order and the number of unpaired electrons. So there's 2 ways that we can approach the question. I mean, they're going to give us the same answer, and it's really the same thing. It's just kind of up to you how you want to remember these things. So I think it's always helpful to think about the full diagram, and this will at least give us an idea for where these different orbitals come from. So when we have O2, we have valence 2s orbitals, eventually, once my tablet lets me write again. We have 2s orbitals that are going to be valence orbitals in each oxygen. So when we draw a molecular orbital diagram, we put the atomic orbitals on the outside. So we have 2s for oxygen. I should probably widen this a little bit in the middle of everything. And then we also have 2p. So a set of 3 2p orbitals, just like we talked about a little bit earlier. You always have 3p orbitals at the same energy. And then we're going to mix these together to form molecular orbitals. So these are the individual atomic orbitals. We're going to mathematically combine those to form molecular orbitals. So for the s orbitals, we have 2 orbitals. We get one that's lower in energy, which is a sigma. Then we get the antibonding orbital, which is higher in energy. That's going to be sigma star. And then in the p orbitals, we form 2 different kinds of orbitals. So for O2, it's going to be, the sigma is going to come first, and then the pi. So we get a set of bonding orbitals. One of them is going to be sigma, and that's going to be our lower energy one for oxygen. And then we also have pi. Which is going to be the next one. So we have sigma and then pi. These are both bonding orbitals. So we have 6 p orbitals. 3 of them go down in energy to form bonding combinations. And then we also have the anti-bonding pi star and then sigma star. All right, so that's the order of the orbitals from lowest to highest, and this is sort of the atomic orbital parentage that they come from. The other way we can remember this, if you want to just memorize the order of the orbitals, is just remember what we're going to be doing is adding electrons to these. So we have the order of the orbitals for oxygen is sigma 2s, sigma star 2s, that's lowest energy to highest energy, sigma 2p, pi 2p, pi star, sigma star. So whether you want to think about the full diagram here, or just remember the order that the orbitals come in when you form molecular orbitals, that's fine. The part that we have to be a little bit careful with is when we're in the second half of the p block, so when we're with oxygen, fluorine, neon, so P4, P5, P6, this is the correct order for these 2 orbitals. When we have boron, carbon, nitrogen, the first half of the p block, these 2 orbitals switch their order. So however you choose to remember this, you have to remember that for the first 3 p elements, group 3, group 4, and group 5, these orbitals are going to be switched, where the pi is going to come first and then sigma. The rest are all in the same order. But this is the correct order for oxygen. So now we have to figure out how many electrons there are. So if we have O2 plus, we have each oxygen has 6 valence electrons. It's a group 6 element. But there's a cation, so we have to subtract 1. So this is going to give us a total of 11 valence electrons. So now our job is to populate this set of orbitals, either written in the diagram like this or just a list of orbitals, with 11 total electrons. Remembering that the sigma orbitals are singly degenerate, so they can each take 2 electrons. The pi orbitals have a degeneracy of 2, meaning there's 2 at the same energy, and so for each pi set we can put a total of 4 electrons in there. Alright, so let's go ahead and do this, and then for using this diagram here, we have 11 electrons. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the 11th goes up there in the pi star. So we fill the orbitals lowest to highest using Aufbau principle, Hund's rule, things that are exactly like we did for atomic orbitals. That gives us this diagram here. If we want to start putting these into here, each sigma gets 2, so it's going to be 2, 4, 6, and then we get 4 for the pi. That takes us up to 10, and then the last one goes in the pi star. Okay, so that's the electron configuration. That's just translating this into more of a electron configuration. Now the 2 questions that it asks us are bond order and number of unpaired electrons. So the bond order is, remember, 1/2, and then we have to count the number of electrons that are in bonding orbitals first. So we have 11 total electrons, and we find the ones that are in bonding orbitals. We have 2 that are in the sigma 2s, 2 more up here, and then 4 in the pi 2p. So 2, 4, 6, 8 of our 11 electrons are in bonding orbitals. And if there's 8 in bonding orbitals, the other 3 must be anti-bonding. So we have these 2 here that are in sigma star, and this one that's in the pi star. So the rest of our electrons are in anti-bonding orbitals, and that gives us a bond order of 2.5. So remember that molecular orbital theory allows us to predict fractional bond orders, which is not something that's really easy to do with valence bond theory. And so we predict a bond order of 2.5 for this, and then the number of unpaired electrons. That's where having this type of diagram is helpful, because we have to recognize that there are 2 degenerate pi orbitals and we're counting unpaired electrons. In this case it doesn't really matter, but you see that there's just this single unpaired electron. The rest of them are all spin up, spin down, pair with each other, but that last electron goes into our own orbital and is unpaired. So there's one unpaired electron. The maximum number of unpaired electrons that you can have is 2, because you could have one electron here, one electron there, which is what you would have for neutral O2. But in O2 with a positive charge, you only have one electron, so only one of those is unpaired. Okay, so questions on that? All right, that's one of the more abstract topics, I would say, but if you can remember these diagrams and know how to fill them with electrons, that's, again, the level of depth that we expect you to be able to do for this. We're not going to go any more detailed than what I just showed you now. Okay? All right, moving on to number 6. All right, so here we're back, we're into chapter 5 topics. We're trying to keep track of where we are in the progress. So we have a hypothetical element that has an atomic mass of 132.2145. If it has two stable isotopes, 131 and 134, I gave you the mass of each of those as well. What is the percent abundance of the 134 isotope? All right, so remember that when we're determining atomic masses or determining abundances of individual isotopes, there's really only one equation we have to remember. So the atomic mass that we report on the periodic table is a weighted average of all of the individual isotope masses. So that's going to be the abundance of one of the isotopes times its mass. So let's say we have isotopes A, B, C, however many we have. So the abundance of isotope A times its mass plus the abundance of isotope B times its mass. And if there's more than two isotopes, you just keep adding them up and up and up. So in this problem here, we're given the atomic mass, and we're trying to find the abundance of one of our isotopes. Let's say that this is 131, this is 134. So we're given the atomic mass, we're given the individual isotope masses, but we want to find the abundance of one of the isotopes, which is our unknown. So let's call those, to make things a little bit simpler, X and Y. Let's call the abundance of A X and the abundance of B Y. So we have two isotopes with their abundances unknown. Now we should recognize we only have one equation and we have two unknowns, so that's a bit of a problem, but then always keep in mind that the sum of the abundances, however many there are, has to equal 1. These are fractional abundances, so the sum of those two equals 1. So we have two equations now with two unknowns. Let's call the one that we're solving for Y. That's going to be the abundance of the 134 isotope. So we can rewrite this equation by solving for X. X equals 1 minus Y, taking this and putting it up here to give this a single variable. All right, so the atomic mass that we're given, 132.2145, is equal to the mass of the first isotope times its abundance. So the mass of the 131 is given as 130.9856. Its abundance, when we rewrote this equation, is going to be given by 1 minus Y, which is what we're solving for. The abundance of the second isotope is 133.9767, and that's the mass of the second isotope, and its abundance is given by Y. So this is the equation we have to solve for Y. So Y is going to be the abundance of the second isotope, 134. And when we solve for this, we get 0.4109. Now keep in mind that the question is asking us for what is the percent abundance. So anytime we have percent, we have to multiply by 100. So the percent is going to be that number times 100. So the total percentage will be 41.09%. All right, so that means in a natural sample of this fictitious element, 41% is going to be the isotope 134, and the rest of the 59% is going to be the other isotope 131. Okay, so whenever you have individual isotope masses, you can use the weighted average to find the atomic mass. It's just one equation we have to worry about, but then we have to sometimes solve for different unknowns depending on how the question is set up. All right, questions on that one? Okay. Number 7. Now we're into topics related to moles. We've been using moles, these concepts a lot in recent weeks, so a lot of this stuff, hopefully towards the beginning of chapter 5 is becoming a little bit more routine for us. So this one we have here, we have 65.65 grams of sodium phosphate, and we want to know how many moles of sodium ions are present in that sample. All right, so sodium phosphate is made up of sodium and phosphate. So the first thing we need to have is the correct chemical formula. Anytime we're trying to convert masses into moles, we need to know the molecular formula or the chemical formula. So we have sodium plus, phosphate, remember, is PO4 3 minus. So even though these polyatomic ions are technically a chapter 3 topic, they are going to come back again and again. So we have to know the formulas and the charges for all of our polyatomics. So we have sodium, phosphate, and so when we want to balance the charges here to make a neutral ionic compound, the correct chemical formula for sodium phosphate is Na3PO4. All right, so that's the first step, is to get the chemical formula. We will also then need the molar mass of this, because if we're trying to convert grams into something related to moles, we need the molar mass, which is the mass of 1 mole. So remember, when we calculate the molar mass, which is often abbreviated MW for molecular weight, which is synonymous, we just take the sums of the individual atomic masses. So we have 3 sodiums, and if we go to the periodic table, sodium has an atomic mass over here of 22.99. Okay, so the mass of sodium is 22.99, and there's 3 of them. I'll be a little bit sloppy and leave out units, but they're all grams per mole. We have 1 phosphorus, so that's the mass for sodium. 1 phosphorus, the mass of phosphorus is 30.97. And then we have 4 oxygens, and from the periodic table, the mass for oxygen is 16. So the molar mass of this compound is 163.94, and the units, of course, are grams per mole. So this is the molar mass for sodium phosphate. So that's going to help us when we're trying to convert into the moles of sodium ions. So let's go ahead and set up the question now, or the problem now that we have all the numbers we need. So we're looking for moles of sodium ions, which is Na+. So we have 65.65. Sorry, I thought I saw a mouse again. It was just this thing dangling. Probably had a heart attack again. All right, 65.65 grams of sodium phosphate. And then we want to convert into moles, so we use the molar mass. 1 mole of sodium phosphate has a mass of 163.94, so we want to divide by that to cancel out grams. Now, very often people will stop here, but this is where it's helpful to label everything very clearly. This is the number of moles of sodium phosphate we have, but we're looking for the number of moles of sodium ions. Okay, so remember, we have to then take one more step, which is if we look at the chemical formula, Na3PO4, there's going to be 3 sodium ions per mole of sodium phosphate. That's what the chemical formula tells us. So this last step here is the one that the vast majority of people forget when they get this problem wrong, and it's going to be 3 moles of Na plus for every 1 mole of Na3PO4. Okay, so we have to include that last step. And so when we multiply this out, we get 1.201 moles of Na plus. And if this was a Blackboard problem, of course, you would just enter the number. I think we all got the hang of that, but remember, don't put units in Blackboard. We won't ask you for units, just enter the number. And that's going to give us then the moles of sodium ions, which is going to be related to the moles of Na3PO4 by that conversion. Yep.
Why don't we have a 3 in front of sodium?
The 3 in front of sodium?
For the, on the reactant side.
Well, this is not really a reaction. This is, what I'm showing you here is just how we got the chemical formula. So we have those 2 ions combining, and remember that when we find chemical formulas, we put the charges down as subscripts. But yes, if we were talking about the formation of that from the ions, or the dissolution of this into ions, then yes, if it was written as a chemical reaction, there should be a 3 in front of sodium. So however you want to think about it, that's another way to sort of think about it. There has to be 3 moles of sodium for every mole of sodium phosphate that you have, which comes directly from the subscripts in the chemical formula, or if you were to dissolve that in water, you would always release 3 moles of Na plus for every 1 mole of sodium phosphate that you dissolve. Other questions? All right, so then taking it a little bit further now, we have a mass percent problem. So here we're giving you don't do that. We're giving you a compound called catechol, which is 65.4% carbon, 5.49% hydrogen, and 29.1% oxygen by mass. What is the empirical formula? So remember, the empirical formula is the lowest whole number ratio of moles of each element in the compound, and they should all be whole numbers. So right away we can eliminate choice D because they all have to be whole numbers, and choice D has a subscript of 0.333 on oxygen. So that one's not even going to be a valid answer, but the rest of these we have to figure out what's the correct answer. All right, so if we do this, remember that when we're given mass percents, we assume that we have 100 grams of compound, and then we convert each of those amounts into a number of moles. Just give me slow. All right, so we assume 100 grams of compound, and then if you make that assumption, then all of these, all of these percentages are going to be mass amounts. So if we have 100 grams of compound, that means we have 65.4 grams of carbon, 5.49 grams of hydrogen, 29.1 grams of oxygen. So we just use those masses to find moles. So the moles of carbon, if we have 65.4 grams, we just use the atomic masses from the periodic table to convert grams into moles. So for carbon, that's 12.01. And so this corresponds to 5.45 moles of carbon. Moles of hydrogen is 5.49 grams of hydrogen. That's hydrogen atoms, and we convert that into moles using its atomic mass, which is 1.008. Okay, there's grams of hydrogen to moles, so moles of H. And then finally, we do the same thing for oxygen, which is 29.1%, or 29.1 grams, in our assumption of 100 grams of compound. Of 1.82. All right, so we have the moles of each element, which we got from the masses, and then that's going to give us the empirical formula. But remember, we want to convert those all into whole numbers. So if we have C 5.45, H 5.44, and then O 1.82, we have to divide all of those by the smallest one to get them down to whole numbers, or at least get them closer to whole numbers. So we divide each of these by 1.82, which is the smaller number, the smallest number, and that gives us C3H3O. All right, which corresponds to choice A. A common mistake that people make in these problems is doing too much rounding. So in this case, it didn't really matter. As soon as we divide these, we get pretty much whole numbers, C3H3O. But let's say we had instead got in C 1.5, H 1.50. Sometimes you'll divide these and you'll get fractions at this stage still. The biggest mistake people make is rounding these and saying, oh, that's going to be C2H2O. Remember, unless you're really close to a whole number, you don't want to round it. You want to multiply it by some factor. So if this was the answer, and this is not the answer, I'm just giving a hypothetical here, we have to multiply this by 2, and that correct one would be C3H3O2. Okay, so don't do too much rounding in these problems. When you get down to these coefficients here, unless they're really, really close to a whole number, these ones are all within, I think, 0.01 of being exactly 3, then you don't have to worry about any, you can do rounding. But if they're far off from a whole number, like you get 0.5 or 0.33 or 0.25 or something like that, make sure you multiply the whole formula by a small whole number to give you then the smallest whole number coefficients that actually match that ratio. Okay, questions on that? Okay, number 9. Here's just a balancing problem. So we have the reaction of C12H10O with O2 to make CO2 in water. Alright, so this one is not too bad to balance, I don't think. Okay, so those are the reactions and products. We should recognize this as a combustion reaction, and what I like to do for combustion reactions is set this to 1. It says, carbon, hydrogen, and oxygen. Let's set that to 1. And then the first thing you want to do is balance the products based on how much carbon and hydrogen you have from your reactant. So we have 12 carbons in our reactant, so that means we need to have 12 carbons on the product side, so we put a 12 in front of CO2. We have, this is pretty sloppy, let me fix that. We have 10 hydrogens in our reactant, and then we're going to need a 10 on the product side, so we put a 5 in front of H2O. So now the last thing we want to do is balance oxygen, because oxygen appears in 4 different places. So if you have something like that appears in multiple places, you typically want to balance that last, because everything we do to these coefficients for these is going to affect the number of oxygens that we have. But now we've balanced all of them except for O2, so we can use O2 to figure out what we need to have to make sure that the number of oxygens is the same on both sides. So on the product side, as we have it currently written, we have 12 times 2 plus 5, that's a total of 29 oxygens. Over here we have 1 oxygen, so we need 28 more oxygens to be able to balance out the reactant side. So we have 29, we need over here, we have only 1 over here, so we need 28 more. So we put a 14 in front of O2, and now we have a total of 29 on each side. All right? So then this question asks for the sum of the coefficients. Okay, so remember that when we have coefficients, we don't usually write the ones. So normally you would see it written like this. This is a coefficient of 1 if it has nothing in front of it. We have 14 from oxygen, 12 from CO2, 5 from water. So those add up to give us 15 plus 17 is 32. All right, so the correct answer is 32. Sum of all the coefficients. All right, we'll get more into balancing equations later on when we start talking about redox reactions and things like that. But there might be some questions on there where we just give you some random chemical reaction. You have to balance it by inspection, where you just have to make sure that the number of atoms on the reaction on the product side matches. Okay, questions on that topic? Okay, number 10, getting to the halfway point. We have 3.25 grams of butane, which is burned, synonym for burning is combusting, in the presence of excess O2. What is the mass of CO2 that forms in grams? So combustion is one of those reactions where you're going to have to understand what the reactions and the products look like for that. This is one where we don't give you the chemical reaction and you have to write it yourself. So remember that for combustion, you're taking your compound, usually carbon, hydrogen, maybe some oxygen in it. So the last example was a combustion reaction. Here we're going to write the combustion reaction for C4H10. So when you have a combustion, your other reactant is always O2, and the only 2 products you have are CO2 and water. This is called a complete combustion. Okay, so all of this gets converted into water and carbon dioxide. And so now we have to balance it the same way that we did the last one. So we have 4 carbons in our reactants, that makes it 4 CO2s. We have 10 hydrogens in our reactants, that makes 5 waters. And then if we want to balance the oxygen, which doesn't matter so much for this specific problem, but if we want a fully balanced reaction, we have 8 plus 5 is 13 oxygens on our product side, so we have to put a 13 halves for O2. For stoichiometry problems, which is what this is, we're trying to find out the mass of one of the products that forms. It doesn't really matter if you have fractions here or not. It'll work the same way. But if it's more comfortable for you to work without fractional coefficients, the way we would deal with that is we take this whole thing and multiply it by 2 to get rid of that 2 in the denominator. And so the lowest combination of whole number coefficients would be 2 C4H10 plus 13 O2 to give 8 CO2 and 10 water. You can use any form of the balanced reaction you want to do a stoichiometry problem as long as it's properly balanced. So this is fine, this is fine. You could have doubled the coefficients from here. It really doesn't matter as long as they're balanced. But I think it's comfortable to work without fractions, so I'll use this form of the reaction here when I'm setting up the problem. So we're looking for the mass of CO2 that forms when we burn 3.25 grams. So this is a pretty typical mass-to-mass stoichiometry problem. We have 3.25 grams of our reactant, which is butane, C4H10. When we're doing stoichiometry, the first thing we should always think about doing is converting to moles. So the molar mass of C4H10 is given to us as 58.14. So if we divide by that number, that converts grams into moles. So now that we have moles of C4H10, we're looking for the amount of CO2 that forms, which is one of our products. Here's where we use mole ratios that come from the balanced coefficients. So we have 8 moles of CO2 that form for every 2 moles of C4H10 that reacts. Or alternatively, we're using this form in the equation, 4 moles of CO2 for 1 mole of C4H10. The ratio is still the same. So we're going to say that 8 moles of CO2 forms for every 1 mole of C4H10. So moles of C4H10 cancels out, and we get to moles of CO2. And then the last step is to convert that into grams. So now that we have, and this time I brought my charger. I make a lot of mistakes, but I don't typically make the same one twice. So let me get this plugged in before it dies. Yes. Let me make sure this is charging. Yes, good. All right. So there's a 2 there. Sorry about that. And then we have to convert that into grams of CO2 by using the molar mass of CO2 to get back into grams. So 44.01 grams of CO2. I guess I didn't give you that molar mass, but that's the molar mass of CO2, and that's per mole of CO2. So moles cancel out, and we're back in grams, and that comes out to 9.84 grams of CO2. And again, if this was a blackboard problem, you would just enter in the number, leaving the units out. Okay, questions? All right, we probably have a few more of these that deal with stoichiometry, so we'll get some more practice on this. What is the percent yield of the reaction shown below if 29.6 grams of gold are combined with 50 milliliters of 4 molar HOCl in the presence of excess HCl, and we form 33.9 grams of gold chloride? All right, so there's a lot of information here, but keep in mind that what we're looking for is percent yield. All right, so it's always helpful in these long problems like this to zoom in on what the question is asking you for, because sometimes we'll give you a lot of information. Some of it may not be 100% necessary in all cases, but look at what it's asking. So it states right at the beginning, what is the percent yield? And we're given the mass of gold chloride that forms, AuCl3, so we're going to find then we need the actual yield of AuCl3 divided by the theoretical yield times 100. So we need both of those numbers to be able to calculate percent yield. The actual yield is the amount of gold chloride that we actually form, which is given to us in the problem, is 33.9 grams. So we're told that that's how many grams we obtained as the product. We want to figure out then the ratio of that to the theoretical yield, the maximum amount that can form. All right, so if we look at the given information here, we're also told that HCl is in excess, so we don't have to worry about calculating the number of moles of that. But then we're given the amounts for 2 different reactants. We have 29.6 grams of gold. This is 50 milliliters and 4 molar. So we have 50 milliliters of that as a solution, and the molarity is 4. And then we're told that we're forming 33.9 grams. So because we are given amounts for both reactants, this is a case where we have to find the limiting reactant. We don't know which of these, whether it's the gold or the HOCl, which is the hypochlorous acid, which of those is going to limit the amount of product that forms? Because the theoretical yield that we need to calculate to do this calculation up here, that's going to be determined by the amount of limiting reactant that we have. So if we have amounts for two reactants or more than two reactants, we have to figure out which one is going to limit the amount of product that forms. All right, so then to do that, we have to find the moles of each reactant first. So this is the method I like to use to figure out limiting reactant. So the moles of gold, we have the mass of that. .6 grams. Gold is an element, so we just need the atomic mass of gold from the periodic table. Let's make sure we know where to find it. So gold is way over here, number 79. And the atomic mass is 196.97. That's the mass of 1 mole of gold. So we use that atomic mass to calculate the moles of gold that we have. So we have 0.150 moles. And then remember, when we want to find what the limiting reactant is, we have to look at what's called the stoichiometric ratio, which is that number, 0.15, divided by the coefficient in the balanced reaction. Alright, so luckily we were given a balanced reaction, but our gold has a coefficient of 2 in front of it, so when we want to find the stoichiometric ratio, it's going to be 0.015 divided by 2, or 0.075. And then we do the same thing for the other reactant, which is this hypochlorous acid, HOCl. However, in this case, we're not given a mass, we're given a volume and a molarity. So this is another conversion we have to be able to do to find moles. So this is a combination then of a stoichiometry problem that involves mass and a stoichiometry problem that involves molarity. And so for this one, we have to use the molarity and the volume. So the moles of HOCl, we have 50 milliliters of solution. And then remember that this 4.00 molar tells us that there are 4 moles per liter of solution, or 4 moles per 1,000 milliliters. So we can use that as a conversion. 4.00 moles of HOCl for every 1,000 milliliters. And so that gives us 0.200. And then the stoichiometric ratio for this is 0.200 divided by 3. So this one has a coefficient of 3 in the balanced reaction. So we divide that number by 3, and we get 0.067. So remember, the smaller of the two is the limiting reactant. So this HOCl here has a smaller stoichiometric ratio, so it's the limiting reactant. Okay, so that number tells us that this is limiting reactant. So when we calculate the theoretical yield of gold chloride, which is the other thing that we need to do now, we have to start with that amount. So remember, we start with the moles of limiting reactant. We have 0.2 moles of HOCl. So we're going to use that to find the mass of gold chloride that can theoretically form. So for the theoretical yield, we start with the moles of our limiting reactant, which is 0.2. That's HOCl. Sorry. We have moles of our reaction already, so we use mole ratios to find the amount of product that can form. So from the balanced reaction, 2 moles of AuCl3 forms for every 3 moles of our limiting reactant. And then we need to find the mass of our product that can theoretically be formed. So the molar mass of gold chloride is given to us as 303.32. So we multiply that to get back into grams. Coming down here, that's going to be 40.4 grams. Alright, so that's our theoretical yield, the maximum amount of gold chloride that can form. And then finally we just have to divide the two to get the percent yield. So the percent yield, I'm running out of room here. Our actual yield is 33.9 grams. Our theoretical yield that we just calculated is 40.4. We multiply that by 100 to get a percent, and that comes out to 83.9. This one it's to 2 decimal places, so we'll keep 83.90, and that's going to be the number we would enter in. So this is the percentage of product that we form relative to the maximum amount that can form. All right, so there's a lot of steps involved here because we have to first find the limiting reactant, use that to calculate theoretical yield, and then we can finally divide the two. So questions on that one? Yeah. For the limiting reactant, the first R is 0.075. So that's taking the moles dividing by the coefficient for each one of them. So find the moles of each and divided by the coefficient, and that's 0.075, 0.067. That one's a little bit smaller, so that's going to be our limiting reactant. It's going to limit the amount of product that can form. Okay. All right, number 12, we're now squarely into Chapter 6 topics. So which of the following aqueous solutions would not conduct electricity at all? So remember that when we have aqueous solutions, there are basically 3 different types we can have. We have strong electrolytes, weak electrolytes, and non-electrolytes. All right, so those are the 3 possibilities: strong, weak, and non-electrolyte. These two here, the ones that are classified as electrolytes, whether they're strong or weak, these ones conduct electricity. Strong electrolytes conduct it better than weak electrolytes, but they both do conduct electricity. So those are the 2 types of solutions that conduct electricity. Non-electrolytes do not conduct electricity at all, okay? So those are the 3 possibilities. 2 of them conduct, 1 of them does not. Now, what types of compounds do we have that are classified as strong, weak, or non-electrolytes? So strong electrolytes are going to be either soluble ionic compounds or strong acids. Those are both categorized as strong electrolytes. And then for weak electrolytes, really the only type that we're going to deal with are weak acids or weak bases. There's only one weak base we should be familiar with, which is NH3. But weak acids are also weak electrolytes. And then non-electrolytes are going to be soluble covalent compounds. But these ones are going to be ones that are not acids or bases. All right, so we do have to be able to recognize which compounds are acids and bases to be able to do this, but any covalent compound that's not an acid or a base is going to give us a non-electrolyte solution. Because when that dissolves in water, it doesn't release any ions. It just gets solvated by the water, but the molecule is still intact, and there's no charged species to carry electricity. So then we have these 5 choices here. We're going to look for the one that would not conduct electricity, so we have to categorize all of them. So HNO3, remember, is a strong acid. Anytime we have hydrogen at the beginning of the formula and it's paired with an anion, it's going to be an acid, and then HNO3 is one of our 6 strong acids that we should know. Calcium chloride is an ionic compound. The question is it soluble or not? So chloride salts tend to be soluble, so calcium chloride is soluble. There's only a few exceptions for insoluble chlorides. So this is a soluble ionic compound, so both of these first 2 would be strong electrolytes. H2CO, so that's going to be a covalent compound. It's not an acid. Actually, remember, there is no HCO minus anion, and the hydrogens are bonded to carbon. So anything that has hydrogens only bonded to carbon is not an acid. And here we have, again, there's no anion that this is paired with. It's just a covalent compound. KOH is an ionic compound that's soluble, and H3PO4 is a weak acid, so it'll give a weak electrolyte solution. So the only one of these, which is a covalent compound and not an acid, is going to be choice C, H2CO. Okay? So the acid, we should definitely recognize the familiar acids. We're not going to give you one that's off the wall and expect you to predict it, but the acids are going to be things like there's oxo acids where you have hydrogen paired with one of these polyatomic anions like HNO3, H3PO4, or if you have, HF, HCl, HBr, HI, those ones are also common acids. But most other things are just regular covalent compounds, especially if the hydrogen is bonding to carbon like it is in H2CO. All right? Yep. Yes, but all strong bases are soluble ionic compounds, so it's kind of redundant to put it as a separate category. Because the strong bases that we have are things like KOH, which are salts of hydroxide, which are also soluble. So they're really the same thing. Yeah. But not all, of course, not all ionic compounds are bases, but all strong bases are soluble ionic compounds. So that's why we don't have a separate category. But that is true; they are electrolytes. Questions other than that? All right, number 13. So here we're talking about more quantitative aspects of solutions. So we have a solution of 25.65 grams of calcium perchlorate. Now we want to know what is the concentration of perchlorate ions in molarity. So this one has some similarities to one of the problems we saw much earlier, which is relating, chemical formulas and masses into, number of moles. But there's a little bit of additional step we have to take here because we're looking for molarity, not just number of moles. So, like we said before, if we're given a mass of compound, we have to be able to find the chemical formula to be able to convert it into moles. So if we have calcium 2 plus, that's going to be calcium. Remember, calcium is in group 2, so it's going to be a plus 2 cation. And then perchlorate is one of our polyatomic anions that we should know. It's ClO4, and then the charge is going to be -1. So you have calcium 2 plus paired with perchlorate, so then the formula for this would be calcium and then perchlorate taken twice. Okay, so that's the correct chemical formula for calcium perchlorate. And what we're looking for here is the molarity of perchlorate ions when we dissolve that much calcium chlorate in 1.23 liters of water. So molarity is defined as moles per liter. So we're looking for the moles of perchlorate divided by the liters of solution. So one of these is given to us. We see in the problem that we're making a solution that has 1.23 liters as the volume, so that's going to be what we divide by. We don't have to calculate that number. But then we need to find the moles of perchlorate, and this is going to be an almost identical calculation to the one we did at the very beginning of this review, or I guess not very beginning, but earlier in this review, where we wanted to calculate the moles of ions. So the moles of perchlorate, we're starting with 25.65 grams of calcium perchlorate. I gave you a little bit of a hint for its formula because I gave you the molar mass, which is 238.98. So if we divide that number by the molar mass, we get the number of moles of calcium perchlorate. But then remember, since we're carefully labeling things here, this is moles of calcium perchlorate. We're looking for moles of just perchlorate. And if we look at the chemical formula, there are 2 perchlorates per mole of compounds. We have to multiply them by 2 again. Well, last time it was 3, but this time 2 ClO4 minuses for every 1 calcium perchlorate. And so then that gives us 0.2147 moles. So we're going to put that up here into the ratio to get molarity. So 0.2147 moles per liter for 1.23 liters gives us a molarity of 0.175. Alright, so whenever you want to find molarity, we divide moles by liters of solution. And we just have to be careful about what exact molarity are we calculating. We're calculating the molarity of perchlorate, so we need the moles of the total number of moles of perchlorate ions, not just the moles of calcium perchlorate. Okay, questions on that? There's a lot of overlap with the earlier problem, but this just then introduced the definition of molarity as well. Okay. On number 14, we have something else that we can do with molarity, which is called dilution. So here we're taking we have 125 milliliters of water, which is going to be added to 225 milliliters of a 0.254 molar sodium chloride solution. What is the final concentration in molarity for NaCl? So we're assuming the volumes are additive, and we're going to calculate the answer to 3 decimal places. So we should instantly recognize dilution problems by a few key words. So when we're doing dilution, all we're doing is we're taking the solution of a compound and we're adding water to it to make the concentration different. So when we're doing dilution, we're not reacting with anything, we're not doing any sort of conversion or transformation. It's just adding water to change the concentration. So you only have one substance you're dealing with for dilution. Because sometimes people try to use the dilution equation in other situations when it doesn't apply, and you can run into trouble there. But dilution is specifically just changing the concentration of something by adding water. So the dilution equation is M1V1 equals M2V2. So we're given the initial volume and molarity. We have 225 milliliters to start with, and the concentration is 0.54, so that's our initial molarity. But we're looking for the final molarity, which is M2. So that's going to be M1V1 over V2. So we have the initial molarity and volume M1V1, but we need to find V2. Now remember that in this equation, the volumes are the total volume of solution before and after the dilution. It's not just the amount of water that you're adding. So when we want to find V2, it's going to be our initial molarity, our initial volume 225, and then we have to add the 125 from the water that we're adding. So in this equation, M1V1 equals M2V2, the volumes are the total volumes. So when you do a dilution, it's going to be the sum of the volume of solution that you combine with the volume of water that you combine. So don't be fooled by that one here. So it's 350 milliliters is the final volume. And so then when we put the numbers in, we have 0.254 molar. We can use whatever volume unit we want as long as they're the same in the top and bottom. So we're starting with 225 milliliters. We're diluting it to 350 milliliters by adding 125 milliliters of water. So milliliters cancel out, molarity is left, and so that gives us an answer of 0.163 molar. All right, and you should recognize also that if we're doing dilution and we're solving for M2, which is paired with V2, the more dilute solution, you should get a smaller molarity if your final volume is larger. All right, so our final volume is the sum of the two, and then our final molarity then is going to be smaller than our initial molarity because we added water to the solution to make the concentration lower. Okay, questions on that one? Or when to use the dilution equation in general? Okay. All right, number 15, we're going to start talking about types of reactions that happen in an aqueous solution. So here we're looking for which of the following mixtures will not form a precipitate. All right, so remember that when we mix solutions of ionic compounds together, we exchange the ions with each other, and sometimes some pair of those ions is going to form an insoluble ionic compound, which then precipitates from solution. So to answer questions like this, where we want to know whether a precipitate will form or not, or what is the identity of the precipitate, we have to know the solubility rules, which we covered in class not too long ago. All right, so then we have to look at all these possibilities. So what I'm going to do for all of these is just write out what are the compounds that form when we swap the ions. So we have KCl and silver nitrate in the first one. And so we're going to take the potassium, the cation from the first, and pair it with the anion from the second. So it's going to be KNO3 is one of our products. And then the other product, we're going to take the cation from the second compound, Ag+, and pair it with Cl-, which makes AgCl. So these are the two products when we mix those two. And we're going to recognize if any of these is insoluble. So AgCl is insoluble. This is sort of the classic, insoluble halide. So that's going to be our precipitate. KNO3 is going to remain in solution because all potassium salts are soluble, all nitrate salts are soluble. So any compound that has either of these ions in it will be soluble. All right, for choice B, we have ammonium sulfate and lead perchlorate. So when we combine the first cation, ammonium, which is NH4+, with the second anion, which is perchlorate ClO4-, we get NH4Cl is one of the products, ClO4. We're not going to worry about balancing these. We just want to identify what the products are. Doesn't matter whether there's a coefficient or not. And then the second product is going to be lead 2 plus mixed with sulfate. So we get PbSO4. And lead is another one where it's going to form insoluble compounds unless it's paired with one of those special anions. So lead and silver, unless they're paired with nitrate, perchlorate, or acetate, those are going to be insoluble. So lead and silver halides are insoluble, lead and silver sulfates are insoluble. Anything else besides those few exceptions are going to be insoluble. So this forms a precipitate, lead sulfate, so that's not going to be our answer choice. Choice C, we're mixing sodium carbonate and barium chloride. So we form sodium chloride and barium carbonate. And again, this second product here, barium carbonate, is insoluble. Carbonate is one of the anions, which is almost always insoluble. So carbonate salts, unless they're paired with lithium, sodium, potassium, rubidium, cesium, or ammonium, one of those group 1 cations, or ammonium, which fits in that same category, all the carbonate salts will be insoluble. So this is an example of an insoluble carbonate. And then finally, choice D, or not finally, we're almost there. We pair these together, we get NaCl, and we get iron hydroxide, which is iron 3 plus. Sodium chloride is very soluble, it has sodium in it, so those are always going to be soluble. But this is going to be an insoluble hydroxide. Hydroxide is also in the category of anions that is usually insoluble. The major exceptions are the alkali metal hydroxides, again lithium, sodium, potassium, and so on, or some of the heavier group 2, calcium, barium, strontium. So most hydroxides are insoluble, and specifically when hydroxide is paired with a transition metal, you know it's going to be insoluble. Finally, the last one, E. So all of these so far have formed a precipitate, so let's see if choice E by default should be the answer. And when we pair these two, calcium nitrate with ammonium chloride, we get calcium chloride and ammonium nitrate. So this one is very obviously soluble because it's ammonium, which is always soluble, it's nitrate, which is always soluble. Calcium chloride, most halides are soluble unless they're paired with silver, lead, and a couple other exceptions. So all of the group 1 and group 2 halides are going to be soluble, so both of these compounds are soluble, which means there won't be any precipitate that forms when we mix these solutions together. So that would be choice E then is the correct answer. It's the only one where the products of the ion exchange do not form something that is insoluble. So you're going to have to commit yourself to learning those solubility rules, but I encourage you to do it sort of the way I went through it in class, which is to kind of rank them in sort of a hierarchy and look for the obvious ones first, the ones that are always true, and then there's obviously going to be some tricky exceptions you have to worry about. But in most cases, you can identify them as one of the obvious ones. So, silver and lead are pretty obvious. Most of those are insoluble. Carbonates are pretty obvious. Most of those are insoluble, and so on. And you have some of those special cations and anions like potassium, sodium, ammonium, which tend to always be soluble. So try to focus at first on the ones that are very obvious before worrying about all the tricky ones. All right, questions on that? Yep. Yes, anything with nitrate in it is soluble. So that's what I called in the notes category A, I think I had it. And so there's a certain list of cations and anions. So the cations are group 1A, all those lithium, sodium, and so on, and ammonium. Those cations plus perchlorate, nitrate, and acetate. If you have just one of those ions in the compound, it will be soluble. It doesn't matter what the other ion is that's paired with it. Yep. Group 1 what? Yeah. No, so if barium is paired with, so if carbonate is paired with a group 1 cation, it would be soluble. So carbonate is an anion that is usually insoluble, and unless it's paired with one of the cations that I mentioned just now, the sodium, lithium, potassium, and so on, those are the only soluble carbonates. So anything else carbonate is with, group 2, transition metal cations, carbonates will be insoluble. So it's always cations and anions paired together. So if one of those cations or anions is in the category of always being soluble, the whole compound will be soluble. So this is a case, though, where this combination gives you an insoluble. Yep. Well, we're not going to worry about slightly or marginally soluble in this course. If you take chemistry 2, so in reality, there's no such thing as either soluble or insoluble. That's a very arbitrary, definition, right? Of what's soluble, what's insoluble. Everything can be dissolved to some limit. Now, I think by convention, the things that we categorize as soluble have solubilities that are, I believe, are greater than 1 gram per liter, maybe, is the cutoff that we conventionally use, but I don't know if that's right or not. And so that means anything that's called soluble means we can dissolve at least 1 gram of that into 1 liter of water. If you can't dissolve that much, then it's classified as insoluble, even though there's going to be some very small, finite quantity that you can dissolve, but it's going to be limited to a very small amount. So everything has a solubility that's defined quantitatively, but you won't really touch that until chemistry 2. I guess, but we won't use that terminology in this test, so yeah. All right, anything else? All right, we're getting there. Number 16. What are the spectator ions when aqueous solutions of barium nitrate and sodium phosphate are mixed together? All right, so to find spectator ions, we're looking for the ions that are dissolved, that are soluble on both sides of the chemical equation, so the ones that aren't involved in forming the product. So here this is another precipitation reaction, so we're taking barium nitrate, which is BaNO3, barium is a +2 cation. We're adding that to sodium phosphate. We saw sodium phosphate earlier, it's Na3PO4. All right, now this is, I'm going to go sort of the long way for finding the net ionic equation, but this is helpful as a review. So then we form the products. We're going to pair barium with phosphate, so we get Ba3PO42 to balance the charges, and we get sodium nitrate. So we first have to put some coefficients in here to balance, so we need to have 3 sodium nitrates. Start with this. We want 3 of these to balance the barium. If we have 3 of those, we need 3 sodium nitrates. And then we need to have 2 of these, that becomes 6. So this one was a little bit trickier to balance, but that's going to be the balanced form. We have 3 barium nitrates, 2 sodium phosphates, and that's going to form barium phosphate and 6 sodium nitrates. All the anions are balanced. Now we have to think about which of the products are insoluble, if any. Okay, so phosphate is another one, which is almost always insoluble. So unless this is paired with sodium or lithium or potassium and so on, anything that's group 2 or transition metal phosphate is insoluble. So that's going to be our precipitate, which forms as a solid. This remains in solution. Sodium and nitrate are both always soluble. Okay, so that's what we call the molecular form of the equation, where we write everything intact. We can write the total ionic equation by breaking up everything that's soluble, everything that has an AQ next to it. We break those up into ions. So when barium nitrate dissolves, we get 3 barium 2 plus, and we have a total of 6 nitrates, because there's 3 of them and each has 2. We have from sodium phosphate 6 Na pluses and 2 phosphates. So all the species on the reactant side are going to be soluble. So we break all those up into ions when they're ionic compounds. Then on the product side, our precipitate we leave intact because that's not dissolved in the solution anymore. And then we get 6 Na plus and 6 NO3 minuses from the sodium nitrates. Alright, so this helps us verify that it is balanced. And then the spectator ions are the ones that occur on both sides of the total ionic equation, the ones that cancel out if we were to write the net ionic equation. So we have 6 NO3 minuses on both sides. We have 6 Na pluses on both sides. So those are going to be the 2 spectator ions, which makes choice B correct. The other way to go about identifying spectator ions is just think about what's the precipitate that forms. So the Ba3PO42 is a precipitate, so those ions are not going to be spectators because they're involved in forming that compound. So whatever the other 2 ions are, sodium and nitrate, which is left over, those are the spectator ions. So you don't have to necessarily write out the whole thing if you don't want to, but remember that the spectator ions are dissolved aqueous species on both sides of the chemical equation, and they're not involved in forming the precipitate. So those are two ways you can identify what the spectator ions are. Okay? So if we wanted to write the net ionic equation for this just to be complete, this would be 3 barium 2 plus 2 phosphates is Ba3PO42 as a solid. This is our net ionic, which we didn't really have to do for this problem, but it allows us to then complete the story and review that. And remember that the net ionic equation does not include the spectator ions, so the sodium and the nitrate, which are not in the net ionic equation, are identified as spectators. Okay, questions on those concepts? All right. 17. All right, what volume of 0.255 molar HCl would be required to neutralize 125 milliliters of 0.242 molar calcium hydroxide? All right, so this is a question where we're reacting an acid and a base. We have HCl, which is an acid, calcium hydroxide, it's a soluble hydroxide compound, so it's a base. We're reacting them with each other. We want to know how much of our HCl do we have to add to completely react with that amount of calcium hydroxide. This is where I caution you not to use the M1V1 equals M2V2 equation. It's very tempting to do that here because we have 2 volumes and 2 molarities that we're dealing with. But this is a chemical reaction, and that equation, sometimes it works, but sometimes it doesn't. So I would just encourage you to get in the habit of not using it for these types of problems. So we're going to set this up as just a stoichiometry problem. We're reacting 2 things with each other. We know how much of one of the reactants we have, and we're just trying to figure out how much of the second reactant do we need to react completely with that. So we have to write the balanced acid-base equation. So it's HCl plus calcium hydroxide. Calcium is 2+, so it's going to be CaOH2. The products don't really matter. If we're doing a titration problem where we're just figuring out how much acid reacts with the base or how much base reacts with the acid, all we really care about are the ratio of the 2 reactants. But we can write out the full equation just to be complete. And so this is going to form water as one of the products whenever we have an acid and a base. And then we form an ionic compound where we pair the cation that's in the base, calcium 2+, with the anion that's in the acid, Cl-. That's going to be calcium chloride. That's a soluble ionic compound, so we write it as aqueous. And then to balance this out, remember that this HCl only has 1 H+. That's the formula, which is HCl. Calcium hydroxide has 2 OH-, because it's calcium OH2. So then to balance this, we need to have equal numbers of H+ and OH- to react with each other. So we put a coefficient of 2 in front of HCl. That also means that 2 waters are forming because we have 2 H+ reacting with 2 OH-. So there's a few different ways to balance these, but I just like to look at the number of H+ and OH- and make sure that they're equal. So if our base already has 2 OH- in the formula, we then need to have 2 H+ to be able to react completely with that. Okay? So that's the balanced reaction. Now we just use it to do a glorified stoichiometry problem. So we're looking for what volume in milliliters for HCl. So we're looking for the milliliters of HCl solution that are reacting. So when we're doing a problem like this, a titration problem, we always want to start with the species where we know the volume and the molarity. So for calcium hydroxide, we know that we have 125 milliliters, and we know the molarity is 0.242. So that's going to be our starting point. We have 125 milliliters of that solution. And remember, when we have volumes and we have molarities, we can use that to find moles. So just like any stoichiometry calculation, the first thing we should think about is calculating moles. So we use the molarity, which is 0.242 moles of calcium hydroxide for every 1,000 milliliters. So that gets us into moles of calcium hydroxide, and then we have to find, eventually we're looking for the volume of HCl. We have the molarity of HCl, so let's first calculate the moles of HCl. So here we use the mole ratios from the balanced chemical equation. 2 moles of HCl reacting for every 1 mole of calcium hydroxide. So we want HCl in the numerator, and then we have 1 mole of calcium hydroxide as the denominator. These are just the coefficients from the reaction. Now we have moles of HCl, and the last thing we can do is we know the molarity of HCl, so we can use that as a conversion factor to go back into milliliters. So if the molarity is 0.255, that means there are 0.255 moles in 1,000 milliliters. We want the moles to cancel, so we're going to divide by that number. So we have 0.255 moles of HCl per liter, or per 1,000 milliliters, since that's the final unit we want. We can just do that in one step. So moles of HCl cancel out, and now we're in the desired quantity, which is milliliters of HCl solution. And so we get 237.3 milliliters. And again, in a blackboard test, you would just enter the number, 237.3. All right, so these titration problems, they seem a little bit more daunting for whatever reason than stoichiometry problems, but that's all they really are. It's just using molarities as a conversion factor. And then we always have to look at what we're asked for in the problem. So in a titration problem here, we were just looking for the volume of acid that we had to add to neutralize that. In other cases, though, we could use these types of problems to figure out an unknown molarity or to find a molar mass. There's a lot of variations that we've seen in class, so make sure that we review all those possibilities. But really, it's the set of conversions that we're using is all going to be similar, using molarities and volumes to find number of moles and using stoichiometric coefficients to relate moles of one reactant to moles of another reactant. Okay, questions on that problem? All right, on to number 18, the last major topic which we're going to have on this exam. And I'll warn you right off the bat that you're most likely going to have to balance two redox equations, so be ready for that. That's my one hint about the exam content beyond what I've already given you. But the first thing we have is a question just about assigning oxidation numbers. All right, so remember that oxidation numbers is a way for us to keep track of electrons. In redox reactions, we're always going to be transferring electrons between the two reactants. And to understand whether or not something is gaining or losing electrons, we use the oxidation number to help us decide that. So for assigning oxidation numbers, there's a series of rules that I gave you in the notes back when we introduced this topic. I think that was March 10th, if I remember correctly. So in the notes, we talked about how to assign oxidation numbers. And again, just like we saw for solubility rules, it's helpful to look at the obvious ones first. So let's assign the oxidation numbers for all these compounds. We're looking for which ones have the correct oxidation number for nitrogen. All right, so if we look at the first one, which is nitric acid HNO3. All right, there are some elements that are fairly obvious. So if you have hydrogen and it's in a covalent compound, unless it's bonded to itself, unless it's H2, it's going to always be +1. And then same thing, oxygen, unless it's bonded to itself, like hydrogen peroxide or O2, the oxidation number for oxygen will be -2. So those are sort of the two obvious ones. And then nitrogen has a variable oxidation number, so we're going to find nitrogen based on the rest. So the sum of all the oxidation numbers has to equal the charge. Nitric acid is a neutral compound. So we have 3 -2s, we have a +1, so that's -5, so that means nitrogen has to be +5 to balance out all the oxidation numbers such that they equal 0 when we add them together. Alright, so nitrogen is +5 in nitric acid, so that one is incorrect. We're looking for which one has the correct oxidation number. For B, which is NO2, this one's even a little bit easier. We only have 2 elements this time. Covalent compound, there's no oxygen-oxygen bonds. The only one you have to worry about that's an exception to that is hydrogen peroxide. So this is -2 when oxygen is bonded to nitrogen. 2 -2s is -4, so we need a +4 on nitrogen such that the sum of them equals 0. So NO2 has an oxidation number of +4 for nitrogen, so B is also incorrect. For NCl3, so remember that for oxidation numbers we give all the electrons to the more electronegative atom. So if the halogen is the outer atom, which it is in this case, NCl3, chlorine is on the outside, halogens will always be -1 unless they're the central atom, or unless it's an element by itself. So Cl is going to be -1 in most cases, unless it's the central atom. And so if we have 3 -1s, nitrogen has to be +3. So choice C is also wrong because it has it as -3. And then finally, choice D. This is one of our very simple, obvious ones. Anytime you have an element by itself, whether it's just a single monoatomic element, or in this case a diatomic, where it's just 2 nitrogens bonded together, the oxidation number will always be 0. Right? So elements are really the only type of species where you have oxidation numbers equal to 0. So any element by itself, N2, H2, P4, or if it's just like a metal like sodium, potassium, anything that's an uncharged element by itself is going to have an oxidation number of 0. So this one's also incorrect. So none of the above have the correct oxidation number for nitrogen. So all these are wrong in the choice. So it's going to be +5, +4, +3, and 0. Okay, questions on that? We're going to have to see those same ideas then when we start balancing reactions. So for the last two, we're going to balance redox reactions. So we have, I'll have to rewrite this one because I don't have enough room to do everything. We have H plus MnO4 minus plus NO going to Mn2 plus NO2 plus H2. All right, so we want to balance these by finding the coefficients, and then we want to find, what is it, the sum of the coefficients on the reactant side. I know this one is looking for sum of all coefficients. Okay, so these are usually hard to do by just inspection and just by guessing and checking. We have to use the oxidation number approach to help us. So the first step when we're balancing a redox equation is to assign oxidation numbers for every single atom in the chemical equation. So some of these are fairly easy because we have H plus. Anytime you have an ion by itself, it's just equal to the charge. So the oxidation number for H plus is +1. Permanganate is a little bit of a tricky one, but it's one that we'll see a lot in redox equations. So we have oxygen is going to be always -2 when it's in a compound. We have 4 -2s, that's -8. The overall charge is -7, so the sum has to equal -1, so that means we have to have a +7 on manganese. All right, so it's kind of like a little bit of an algebra problem. So we have 4 -2s is -8. What do we add to that to get an overall -1? And that's going to be +7. +7 is the highest oxidation number for manganese, as it turns out. And then for NO, this one's a fairly simple one because in a covalent compound, oxygen is -2. These have to add up to 0, so that makes nitrogen +2. And then finally for Mn2 plus, it's an ion by itself, so that's going to be +2. That's a pretty straightforward one. NO2 we saw in the last problem. We have 2 -2s for the oxygen, and that makes it a +4 for nitrogen. And then finally H2O, we see this one all the time. -2 for oxygen, +1 for hydrogen, sum equals 0. So those are all the oxidation numbers, and then our first step is to identify the ones that are changing. So we see that manganese goes from +7 to +2. So that's a difference of 5 electrons. So we're finding out the number of electrons that are either lost or gained by manganese. Manganese is getting smaller by 5, so it's going from +7 to +2, so that means it's 5 electrons. Technically it's gaining them, although we don't really care for balancing whether they're gained or lost. And then the other species that's changing is nitrogen. Nitrogen goes from +2 on the reactant side to +4 on the product side. So that's a difference of 2, so we have a 2 electron change for nitrogen. And we need these number of electrons to balance. So the number of electrons has to be the same for both what we call half reactions. So the number of electrons that are gained by manganese has to equal the number of electrons that are lost by nitrogen. So the way we do this, we have to find the least common multiple. So if we multiply this by 2, that gives us 10 total electrons. If we multiply that by 5, that also gives us 10 total electrons. And then we add the coefficients accordingly. So we had to double the number of electrons for manganese. So we have to put a 2 in front of each of those species. We had to multiply by 5 the number of electrons that nitrogen is losing, so we have to put a 5 in front of each of those. And then the rest now, which is just water and H+, we balance by inspection. So right now on the reactant side, we have 8 plus 5 is 13 oxygens. On the product side, we only have 10 from NO2, so we have to add 3 more oxygens to balance the products. So we're going to balance water and oxygen, or water and H+ last, and we use water to make sure the number of oxygen is correct. So by adding 3 more oxygens, we now have 13 on each side. We've added 3 H2Os, that's a total of 6 hydrogens, and then those are going to be then a coefficient of 6 in front of H+. So the sum of the coefficients is 6 plus 2 plus 5 plus 2 plus 5 plus 3. That's 10, 15, 18, 23. All right, so we have a total of 23 when we add up all the coefficients. So for redox reactions, the first thing to always do is use the number of electrons that are transferred to balance those species, and then everything else we do at the very end. Okay, questions on that? All right, we'll see one more of these to close out. So we have another redox reaction. We have chromium chloride plus nitric acid forming chromium nitrate, HNO2, which is nitrous acid, water, and HCl. So a lot of different species here. All right, so once again, we have to assign oxidation numbers. For ionic compounds, the oxidation number is just the charge of the atom in that compound. So if you have chromium chloride, which is an ionic compound, chloride is always -1. It's in group 7. And that means the chromium is going to be +2. That's the charge on chromium in this compound. So for ionic compounds, you just have to find the charges of each ion. Nitric acid, I think we saw this in one of the previous problems. So it's +1 for hydrogen, -2 for oxygen, that leaves +5 for nitrogen. If we go to chromium nitrate, one of our first product here, this is chromium paired with 3 nitrates, so that's -3 total. That means the metal is +3. So our chromium has changed to +3. For NO3 minus, each of these is the same as nitric acid. So we have -2 on oxygen. For each nitrate, we have 3 -2s, and then we also have a +5 on nitrogen to give a total charge of -1. So nitric acid, the oxidation numbers for nitrogen and oxygen don't change. If we just lose a proton to make NO3 minus, we're not going to change the oxidation numbers. HNO2, -2 for oxygen, +1 for hydrogen. So we have a total of -3. That leaves a +3 for nitrogen to balance the oxidation numbers and equal 0. Water is our familiar friend, +1, -2. And then HCl. As I said, in covalent compounds, hydrogen is +1. And then halogens, unless they're a central atom, is going to be -1. So the sum of those equals 0 to balance those out. So those are all the oxidation numbers. We notice here that chromium is changing. It goes from +2 to +3. So that's 2 parts. So Cr is going from +2 to +3. So that's 1 electron. And then we have a nitrogen that's changing as well. We have nitric acid going from +5 for nitrogen, and then one of our products, HNO2, has a nitrogen that's at +3. So this is one of those situations, we saw it in class. This is going to be 2 electrons because the oxidation number is changing by 2. But here we also have some nitrogen that's keeping the same oxidation number. So on the reactant side, all of our nitrogen is +5. But on the product side, we have some that's +3. But we also have some that is still +5. So the easiest way to handle this situation is we're going to balance the nitric acid in 2 separate parts. We're going to use the oxidation numbers, the number of electrons, to balance the part that's involved in the oxidation reduction, and then we're going to balance a separate piece of that at the very end by inspection to make sure that the number of atoms balances. So when I do this, I deliberately I'm going to split up the nitric acid into 2 parts. So we have 2 chromium chlorides. We have HNO3, HNO3. One part we're going to balance using the number of electrons. The other part we're going to balance at the very end to make sure that everything else balances. And we form chromium nitrate. I shouldn't have done that yet, sorry. HNO2, H2O, and finally HCl. Okay, so remember, these are the ones that are changing. Chromium is losing 1 electron. Nitrogen is gaining 2 electrons. So we have to double this to make sure that the number of electrons is the same. So now if we double this, we have 2 electrons for each one. And so to accommodate that, we put a coefficient of 2 in front of each chromium species. These we want to keep the same coefficients that they already have because this is already a 2 electron process, so we don't want to adjust those. So one of our HNO3s, we're going to put a coefficient of 1 in front of it. And our HNO2 is also going to be 1. So we've now balanced the number of electrons, and the rest we just have to balance by inspection. All right, so for our second piece of HNO3, we see that we have 2 chromium nitrates, so we have a total of 6 more nitrogens, so we need to have another 6 nitric acids. All right, or alternatively, we have 6 nitrate counterions, so we need to supply those using 6 nitric acids. And then for water and H+, this is going to be a little bit of a challenge. So if we look at the reaction side right now, we have a total of 21 oxygens. On the product side, we have 18 plus 2 is 20, so we just need 1 water to balance that. And then for chlorine, we have 2 chromium chlorides, so we need to have 4 HCl's to balance chlorine. So the rest of this is just balancing by inspection, looking at the number of atoms and making sure it matches up. So we put a 4 in front of HCl to make sure it balances. And then finally, we can simplify this by combining these 2 species into one. So we're going to have 2 chromium chlorides, total of 7 nitric acids. One of them is involved in being reduced. The other one is just to balance the number of nitrogens. The other 6. So we have a total of 7. And then we get 2 chromium nitrates. We have 1 HNO2, 1 water, and 4 HCl's. Okay, so this really follows the same method that we saw before. We balance the species that are losing and gaining electrons first. We balance everything else at the end. And in this case, some of the nitric acid was involved in gaining electrons in the electron transfer process. Some of the nitric acid we balance at the end to make sure that the total number of nitrogens was correct. So any questions on that one or on redox in general? So then the sum of these is going to be 9. That would be the answer we'd put for this question, which is the sum on the reactant side. All right, any last questions before we wrap this up? All right, thank you all for coming. If you have any last minute questions as you're preparing for the exam, please contact me or come find me, and I'll be happy to answer those.